Why Gauss law is so important in your class 12 electrostatic syllabus? As you have seen before, Gauss law simplifies the problems in electrostatics. Charge and electric field, the relationship between them, better established with the help of Gauss law. Gauss law, already I have taken 2 sessions with you. In this session also I am going to discuss Gauss law, but will be a little bit out of the track. Everything will not be asked in CBSE board paper what we are going to discuss today, but the concept I will discuss very important for all other examinations. Some concepts really will enhance your ability in CBSE physics also, but apart from that, this session is going to be very important for you. I request you to stay till the end. Session may be a bit longer, but the concept you will get today, concept we will discuss here today. I am not saying that I am the only person who will be telling you the concept. You are your own boss, you can learn it yourself. I am going to help you. What are the very important concepts you need to revise in Gauss law before you start solving PYQ, past year's questions? I will not discuss any particular questions here, but definitely the concept discussed here will simplify the problem you are facing. You can finish it easily. Hello everyone, MKS here. So this session I am going to discuss Gauss law part 3, where we will find Gauss law application in more details, and I hope you will enjoy the session. Let's start without wasting time. Just go through the problem given here. This is mainly problem solving class. In this figure there are 2 concentric spheres. They are carrying charge 2q and 4q respectively, and the radius I did not mention here. Radius of the first one be r, and radius of second one is equal to say 2r. Here problem is to find the ratio between fluxes through S1 and S2. There is a second part also. The region of space in S1 filled with dielectric medium of permittivity 4, then what will be the flux coming out through this? You know, Gauss theorem is about phi out. Phi out is given by surface integral of E dot ds, which is equal to Q enclosed by E0. How you are going to find electric field? You compare flux, this formula E dot ds, which you have learned before Gauss law, and then you find flux by using Gauss law, Q enclosed by E0. You compare and get the value of E. But only flux calculation, if this is the question, you better apply Gauss law concept. It is charge enclosed by E0. So flux is coming out through the first surface. Let it be phi 1. To the second surface also it is phi 2. Phi 1 and phi 2, they are directly proportional to charge enclosed. Obviously no medium stated means it is filled with air. So phi 1 going to be what? This phi 1 going to be charge enclosed by E0 here. Okay, what is the charge enclosed here? This phi 1, if we find phi 1 going to be equal to Q enclosed by E0. Q enclosed is 2Q, that 2Q by E0. But when you consider the bigger one, this will enclose 2Q, 4Q, wherever you keep the charge. Intentionally I have taken the charge not at the center. I have taken 2Q close to its circumference, 4Q close to its circumference. Symmetry is required definitely, But Gauss law, if you have a Gaussian surface, it is enclosing some charge, then phi coming out always Q enclosed by A0. So through the first surface, no doubt about it, it is Q enclosed by A0, that is 2Q by A0. Second surface encloses two charges, 2Q and 4Q. So this time Q enclosed by E0, this will be 2Q plus 4Q. So this is nothing but 6Q by E0. So what is the ratio? Required ratio phi 1 by phi 2. This is going to be 2Q by E0, that divided by 6Q by E0, that is 1/3. So phi 1 is to phi 2 equal to 1 is to 3. Isn't it? So ratio between two fluxes we got. Next problem, charge Q is placed at a distance L by 2 from the center of a square of side A. You take L. I have taken L already. So you take this side length equal to L as shown in the diagram. This is the square plate. To get that three-dimensional view, I have kept it this manner. So from the square plate, from its center, at a distance L by 2, a charge Q is placed. Question is to find the flux passing through this. Obviously, from Q, the lines of forces are going this manner, isn't it? It is in all directions. Coming this way, some of them are passing through the surface, some of them are not passing through the surface, can go this manner also. Okay, these are not passing through the surface. And this one. And fluxes are going this way also, can come this manner. Okay, if we draw isometric situation, isotropical situation, then situation will be like this. Equal number of lines of forces will pass through unit area placed at some distance away. The question is, what is the flux passing through this plate then? No closed surface is there. First the problem, you think this manner. You have to make it closed, no? Otherwise you cannot find the flux linkage by Gauss law. We are going to apply Gauss law only for this sum. But how do we enclose the charge? Only one square plate is given and the charge at a distance L by 2 above it is given. So what we have to do there? We need a cube of same side length L, which is going to enclose this plate. This plate we are naming as A, B, C, D. And this plate is the lower face of this cube, whose side length is also L. Now, if I keep this cube on it, then this one is fully enclosed in it. So let us bring it there. And then we are getting symmetry. The charge will be lying at the center of this cube of length L. Am I correct? I hope all of you understand. This we want to enclose first. For that, we are bringing this cube here at the place of the square plate. And now square plate going to be a part of it. So this lower plate, lower face will coincide with this plate. And the cube will enclose this square plate fully. You understand? You understand the diagram? Now we have to enclose it. Almost it can be done. Okay. Yeah, it is almost enclosed now. If it is enclosed, then charge will decide where. If it is enclosed, then charge will decide where. The charge will decide at the center of the cube. Agree or not? Charge will reside at the center of the cube. If charge resides at the center of cube, then we can find it easily, because then it is symmetric. Symmetry principle can be used. Symmetry of Gauss law can be used. How? Because total outward flux, the charge lying at the center of wherever, this is going to be Q by E0. If it lies at center, then it is quite obvious that through all 6 faces of the cube, equal number of lines of forces are passing. That's why it is so important for the calculation, for the requirement of the sum, to bring the charge at the center of this cube, whose lower face was the given plate A, B, C, D. It's alright. So 6 faces are there. Total outward flux phi out is going to be Q by E0. So through one face, it is going to be, through this face only, by symmetry and again symmetry. By symmetry, phi through this surface, this face of the cube, is going to be phi out, that divided by 6. We can't do it so easily if the charge is not lying at the center. It lies at the center, that's why. It will be Q by 0 by 6. The value is Q by 6 is 0. Got it? Understand? Charge Q is placed at center of imaginary hemispherical surface. Do you think it's a hemisphere? If you can't think, then I have to bring it here. This is hemisphere. I have taken the skeleton of this diagram here. Okay? We kept charge Q at the center of the hemisphere. Find the flux of electric field due to the charge through the surface of hemisphere. See, again the same problem. All these lines of forces from here going this manner. I'm just drawing a few and try to draw isotropically in all directions. So lines of forces are going this way. But who will account for these lines of forces? Is it related? These lines of forces are related to the problem? Of course related. If there was a sphere, then total outward flux through the sphere will enclose it. That is the condition. Total outward flux will be equal to Q by E0. If no sphere is there, then Gauss law cannot be used. But we have to find flux coming through this hemisphere. Then what to do? For the sake of the problem, we are bringing this sphere. We are completing this hemisphere by joining the other part of it. Completing hemisphere. This part is added over there. In the problem, this part is added. Okay? So when joined with the given one, then it is a complete sphere. And phi out is, Q by E0. So this thing, through this hemisphere only, it is going to be required flux will be Q by E0, that divided by 2, that is Q by 2 is 0. Alright? You all understand? Through the hemisphere, it will be Q by 2 is 0. Now, this concept of the problem I have seen in board paper as well as in entrance exam papers. Find the amount of charge present in a metallic conductor placed in a uniform electric field. This is a metallic conductor. A cube is placed in a uniform electric field. This is electric field. Field cannot pass through a conductor. That's why situation will be like this. But Gauss theorem states that outward flux depends on charge inside. Outward flux is coming. What is the charge over there? What is the charge enclosed here? Phi entering. This I am discussing last few sessions. Phi entering is equal to, phi in equal to E into this surface area. E into A. Phi out is also E into A. Okay. So resultant, this phi is the total flux coming out. So phi out, net outward flux, phi out going to be equal to 0, which is nothing but Q enclosed by E0. Therefore, Q enclosed equal to E0. Such a conductor will not enclose any charge in it. Still lines of forces passing through it. Okay? Understand? So Q enclosed in this conductor. This question has a link with previous ones. It's going to be very interesting question, that there is a small cube of side length, say 2 unit. Okay? 2 unit or 2L. You take 2L. Side length 2L. You can take L also, it doesn't matter. Charge Q is placed at the vertex G of a cube. I did not mention inside or outside or at G only. Vertex G means inside cube, outside cube, very close to G, or on G only. Result not going to differ. You have to find the electric flux through the faces of this cube. It's a challenging question. Electric flux through the faces means it will be through all 6 faces. This charge Q is kept here just at the place of G, it is kept. Now the flux going through the faces of the cube will be different. Not all. This charge Q is held by the surface EHG, this one ABCDEF, this one EHGF. It lies G of this face. It lies at the face G of FGCB. It lies at this face also, HGCD. Okay, these are the faces on which the charge Q lies. So they have similar situations. Symmetry says that lines of forces passing through this, and passing through HGCD will be similar. But these 3 faces are not similar to these. Let me name those faces here. What are those? Not holding the charge Q, it will be ABFE, one face. The other one ADHE, and ABCD. They are not holding the charge. Symmetry principle says that the flux passing through for this group, this system of faces of the cube, if it is phi here, this will be phi here, this also will be phi. Again, symmetry says that if through this face it is phi dashed, through this face phi dashed, through this also it will be phi dashed. Isn't it? With respect to the charge Q, their geometrical positions are identical. Am I clear? So flux will be similar in this case, flux will be similar in that case. But basic problem is how to calculate. By Gauss law, is it possible? Only by Gauss law? Or you have to use some technique of differentiation, integration. You are very good at this, I know. Do you need to apply all these? I am saying no. Just see the 3D diagram I am bringing for you here. That 3D diagram you need. It is made by me previously. So that understanding will not be a problem for you. Now look at the sum. What I did there, you take the side length, 12 will confuse you. Side length of the small cube is L, so this length will to be L, isn't it? What I did there, I have kept the small cube of length L inside this big one. You understand what I said? How did I keep there? I just enclose this cube by putting one cube here that you can see, one cube this side, one cube this side, one cube this side, one cube above, so that it is enclosed fully by the bigger one. I had to make a bigger cube so that the purpose will be solved. Or you can think this manner. There is a small cube placed here. There is a small cube placed here. This is one side. This is one. This is one. So it was one. Now you have taken 4 cubes from this face. From that face, it looks similar. Now, what is the advantage of bringing the larger cube here? I mean, side length 12. Symmetry. Again symmetry. That charge Q lies at the vertex G will be lying at the center of the bigger cube. So this problem is solved. Through the bigger cube, total outward flux is going to be phi out equal to Q by E0. Isn't it? So bigger cube, Q by E0. So bigger cube has how many faces? 6 faces. This is one of the face. This one, ALMI. ALMI. This is one of the face. And in this face only, the face EFBA. Is there any face like that? Yes. This one lies. It's alright. This face also, EHDA. EHDA is this face. This one also lies. Clear? Calculation is very easy now. From G, total outward flux is Q by E0. So flux coming out through ALMI. Through ALMI. This is one of the 6 faces of the cube. This is going to be that phi out by 6. Isn't it? Phi out is how much? Q by 0, that divide by 6. Answer is Q by 6 is 0. Isn't it? Through which face of the big cube? Only through ALMI. It is Q by 6 is 0. But this is bigger. This is 4 times the area of this face. This is clear from the diagram. I hope all of you have understood the diagram. This face is just 1/4 of the bigger face. So how much flux is coming out here? This we have assumed that through this group A, B, E, F flux linkage will be phi dashed all through this. Phi dashed by symmetry will be phi ALMI, that divided by 4. So this is going to be Q by 6 E0 by 4. Am I correct? So this is going to be phi dashed equal to Q by 24 E0. So this group, this system of brother faces, they are all getting Q by 24 is 0. They are all getting Q by 24 is 0. Problem is solved for these faces. Okay? Those faces do not contain the charge Q. What about these? Will you be able to find EHGF, FGCB, HGCD? Use symmetry principle again. Whatever charge passing through those group of surfaces will be same as this. because net flux has to be Q by E0. For that, they also will get by symmetry each phase Q by 24 is 0, because those fluxes, flux from here will pass through this 1/4 area. Flux from this will pass through 1/4 of this surface area. Just little bit you imagine. Then it is going to be the same thing. Q by 24 is 0, not 5. It is Q by 24 is 0. Okay. So I think this is the best explanation for you. By including the charge Q by a bigger cube, then calculate separately. If you face any problem, directly call me or write in the comment box, this part I did not understand. I'll make another session for you. Okay? We are not going to do it for derivation. We are going to do it for the sake of numerical problems asked in various entrance examinations. How electric field due to a hollow cylinder varies, that we want to discuss here. So field, this is a hollow cylinder. It's a large hollow cylinder. Its axis is fixed. Axis is in this direction only. This is the axis. Inside no charge. Charge reside on the surface only. Your problem is to find electric field here at a point inside. That we refer as E in. Then you want to find outside. It is E out. Clear? So there is cylindrical symmetry. For this cylindrical symmetry, we need to take Gaussian surface, which is nothing but a cylinder only. So let us find E in first. Okay? We'll find E in. So this is going to be our Gaussian surface. Okay? For this Gaussian surface, its radius we want to find at a distance r from the axis. So for finding for E in, we use Gauss law. Phi out equal to Q enclosed by E0. But phi out also can be written as what? E in dot ds. ds means that surface area. If you take here, surface area going to be this manner, and here if you take a surface, then this is positively charged. Lines of forces will be radially outward direction. There will be no electric field this way. So ds, the surface area going this manner, and the electric field lines going, no lines of force there, only no charge is enclosed, so no E will be there inside. No lines of force can pass through here. So through the end cap, this will be equal to 0. The way we have seen, we'll see for solid cylinder also. Here it is, electric flux to the end caps will be equal to 0. So phi out will be E in multiplied by this curved surface area. What is the curved surface area? This length of Gaussian surface is finite. Area finite. Gaussian surface always will be a finite dimension. So length of this Gaussian surface you take as L. This one infinitely long. So phi out will be E in into 2 pi RL. Therefore, E in into 2 pi RL you compare with Q enclosed by 0. But Gaussian surface encloses no charge. So E in going to be equal to 0. This will occur till what? E in will be equal to 0 till the radius of the given cylinder. Okay. So electric field will be 0 from 0 to R, because the axis this is our reference line from where distances are being considered. Now our aim is to calculate the field outside the cylinder. Okay, outside the cylinder you draw the Gaussian surface. So to find the strength of electric field at the point P, we draw the Gaussian surface this manner. Enclosing the point P, cylindrical symmetry is there. So Gaussian surface is also cylinder. Its radius of the given cylinder are this one smaller. So phi out will be, by Gauss law, Q enclosed by E0. Line density of charge you are taking lambda. Line density means along length of the cylinder how much charge is there. So Q enclosed will be lambda into this surface area, that is 2 pi RL, that divided by E0. This is by Gauss law. Lambda into 2 pi RL by E0. But phi out, wait a minute, charge enclosed will be not lambda into 2 pi RL per unit length lambda. So over the length it will be lambda into L. Along the length of cylinder it is lambda. So phi out will be lambda into length of this big cylinder, and that divided by E0 phi out. But phi out without Gauss law, you have to compare these two, no, always. This is E out dot ds. Okay, here E out radially outward. The angle between, this is not inward, it will be radially outward. Okay, it is directed radially outward. So phi out, by this calculation, E out dot ds is constant here. So it will be E out ds cos 0 degree, the way you did before. E out is constant, and this surface area will be 2 pi RL. Am I clear? Now compare these two phi outs. Therefore, lambda L by E0 should be E out into 2 pi RL. Clear? So E out will be lambda by 2 pi E0 R. Clear? E out is lambda by 2 pi E0 R. E in is 0. So how to plot the graph here? Graph will be done accordingly. Like if we take electric field along y-axis and distance along x-axis, then till the distance r equal to r, it remains 0. Electric field along y-axis, this is r, till r it will be 0. After this, E out has maximum value when r is equal to r. If you put r equal to r here, E out is maximum. So E max equal to lambda by 2 pi E0 big R. It will be there here. Okay. This is maximum value. Then E out is inversely proportional to distance. So it will fall along radius. Not radius, distance. Distance decreases, its value also decreases. This is the graph of E versus R. Clear? This time you have to find, due to solid cylinder, the volume density of charge is rho and radius is r. You have to take the Gaussian surface both inside and outside. Previous case, Gaussian surface encloses no charge, but here it is there. Charge will decide on the surface as well as over the whole volume. Okay, even at the end caps. Okay, axis of the cylinder you take, this is our reference line from where all distance is to be considered. So I am finding electric field inside now. So you all can see that I have taken the Gaussian surface, this one, this small cylinder. Its distance from the axis is equal to r. Due to all these charges, field will be radially outward there. Whether you are finding inside or outside, it doesn't matter. But it is sure that due to this charge distribution, field will be radially outward. So this small cylinder, its length you take L and radius equal to r because you wanted to find at a distance r. Then E in into 2 pi RL will be phi out. Agree with me? By Gauss law, phi out will be what? Phi out will be Q enclosed by E0. How much charge is enclosed? If the radius is r, it will be pi r square L rho that divided by E0. Isn't it? Phi out will be Q enclosed by E0, that is pi r square L rho. Why? Because volume density is rho. So we have to multiply the volume of the cylinder with rho. This way you get phi out. Now what you do here, normally you compare these two phi. E in into 2 pi RL pi r square L rho by E0. So pi getting cancelled, even 1 r getting cancelled, rho will be there, L is getting cancelled, it is going to be rho r by 2 E0. You can use a vector here. E in vector is radially outward, no? R vector also radially outward you make. Then E in radially outward, a value is given by rho r by 2 E0. Alright. How to find flux then outside this cylinder? Because you are doing application and Gauss law, you are very strong now. So I can explain this method by skipping some steps. My aim is to explain more problems here with you today. So you want to find electric field here, that we are referring as E out. So we need to take this Gaussian surface outside. Any size. You need not take the same size of Gaussian surface. You can take any size. Okay. This time we want to find electric field at P outside. This is E out. So Gaussian surface is taken by using cylindrical symmetry. It is a cylinder of radius r and length we have taken L dash. I am keeping answer in terms of r only. So you find E out. E out has same value. E out into 2 pi r L dash will give you phi out. 2 pi r L dash means this surface area. If you take a surface area here, then field lines are radially outward and area vector this way, ds. Angle between them is 90 degree. So there will be no flux to the end caps. It is to the curved faces only. Here also. The phi out will be 0 through this. Here also phi out will be 0. Isn't it? It will be due to this curved surface only. So E out we got again. Phi out will be Q enclosed by 0. Q enclosed is given by what? Q enclosed, how to find? Volume density is rho. What is its volume? Pi r square L dashed into volume density charge enclosed, that divided by 0. Compare these two. So E out into 2 pi r L dashed going to be pi r square L dash rho by E0. Clear? So L dash getting cancelled here. You are getting E out equal to 1 R is also getting cancelled. Isn't it? Just a minute. Let me check once. This R is not true because the charge is enclosed in this cylinder only. So when you are calculating Q enclosed, it will be due to this inner cylinder only. I mean this given cylinder only. Given cylinder has radius R. So small r won't be there. It will be R square L dash rho. Isn't it? So you take this one as only pi getting cancelled. E out is rho r square by 2 E0 r. This E out is inversely proportional to distance. This is the case. It will. Otherwise, it will be contrary to the electrostatics concept. No, field will fall gradually. Now our problem is to draw the graph of electric field due to this charge distribution. Let me do it here. One very interesting thing is that if we use this expression on the surface, E surface you replace just R by R, rho R by 2 E0. Here also if you replaced R by R, E surface won't change. Rho R square by 2 E0 R. This is going to be rho R by 2 E0. In both the cases it is rho R by 2 E0. Rho R by 2 E0 has maximum value till what distance? R. But before that it is increasing linearly because here E in magnitude is proportional to R. So it increases linearly till what distance? Till the distance R equal to R. Isn't it? And then its value falls gradually with R. Am I correct? So this value is maximum, which is given by rho R by 2 E0. You must be very good in plotting graphs or at least remembering these graphs. Okay? Because options in entrance exam they ask based on this. I am doing here in details because of that reason only. No? It will be straight line inside the volume, outside it changes. Clear? See this problem, electric field strength inside the cavity. I have taken this 3-dimensional diagram for you. Where is the cavity? You try to understand. Cavity is actually this pink portion. This is the whole cylinder. There is a cavity. You have to find electric field strength at a point inside the cavity if a charge is distributed over the volume of the cylinder apart from this cavity part. Cavity means cavity, nothing is there. Charge is also not there. We are not keeping any charge inside. Charge is there over this volume only. Is it clear? You all understand which one cylinder, which one the cavity? Cavity has no charge. The distance between two axes. Let us draw two axes. Two axes are there. AB is one axis and this is another one. Yeah, distance between these two axes is given as A. Your problem is to find the strength of electric field at any point inside this cavity. Not on the axis. Apart from axis of this cavity, we are taking any point in it. Okay? Any arbitrary point. You take an arbitrary point here and consider 3-dimensionally This is the point P inside cavity. This is the point inside the given cylinder also. Only known thing is that volume density and distance between these two. We have to get it in terms of these two things. To solve it, I explained the cavity part. How does a cavity arise inside a charged body? I mean, that portion, cylindrical portion, no charge will decide. It's possible. We dug out the material from there so that the cavity is already there. Cavity can be thought this manner also. Imagine the cylinder is fully charged. I mean, this cylinder had some radius given, say R. Okay. This cavity has some radius smaller, say. So how superposition principle we are going to discuss? We are going to discuss in this manner. We first assume that let the cylinder be charged with volume density rho. And then we take a cylinder of radius smaller whose volume density minus rho. They are superposed. They are pasted at the same place. I mean, that negatively charged cylinder you paste at the same place inside bigger cylinder. No charge will be there. A cavity is formed. Your problem is to find cavity at P. By remembering this formula, due to solid cylinder at a distance R, electric field is rho R by 2 E0, just deduced. We will be using this expression. So, by superposition principle, let us take origin, a point on this axis O1, corresponding point here as O2 on the axis of the cavity. Clear? This point P had some location with respect to the axis. Imagine three-dimensionally. This distance is R1. It has some distance from R2 is there from O2. O2 is just corresponding point on the cavity. Okay. Now, at P, electric field at P, we are using superposition principle. This is equal to EP due to the first cylinder plus this one you are naming as second cylinder, whose volume density is minus rho. EP1 has volume density rho. Okay. EP1 stands for what? Let me write. EP1 equal to electric field at P due to the cylinder whose radius is equal to R and it is imagined that the cylinder has, the whole cylinder, it has volume density of charge is equal to rho. EP2 is what? EP2 equal to electric field at P due to the cylinder of electric field at P due to the cylinder of volume density minus rho. Okay. This one, pink one has volume density minus rho. The whole cylinder positively charged. When they fit together at that place, no charge will reside on the cavity portion. Clear? Now, distance of P from O1, from a point on the axis of the original cylinder, you have taken R1. Let O1P equal to R1 and O2P equal to R2. You agree with me? So electric field at P, I am writing here. Electric field at P, I have written EP1, you write E only, just E vector. EP1 vector plus EP2 vector. EP1 due to the first cylinder, you know the formula, it is distance R1, rho R1 by 2 is 0. This one also you know the formula, it has volume density minus rho. So it will be minus rho into R2 by E0. Agree or not? Minus rho into R2 by 2E0. So rho by 2E0, R1 minus R2. What is R1 minus R2 in this triangle? R1 minus R2 is what? This one we have taken R1, this one R2 and this one A. So in figure, A plus R2 equal to R1 by triangle of vector addition. So the A vector going to be R1 minus R2. Clear? So you just replace R1 minus R2 by A. It is going to be rho A by 2E0. Very interesting. It depends on volume density and distance between two axes. It's an excellent problem. It will help you to think. It will help you to do some sums on your own. Any cylinder, any sphere, if cavity is there, electric field can be determined easily by this vector method. I hope all of you have understood. If you don't understand, what you have to do? Write in the comment, call me directly or send the message in WhatsApp. Now a volume density of charge given. This sphere has radius R and volume density of charge rho. I forgot to write there. Your problem is to find the strength of electric field due to this sphere inside and outside. Got it? Inside means at a point somewhere like this. Any point, arbitrary point. And outside means at some point like this. We have to find. Clear? What do you do there to find electric field inside? Draw the Gaussian surface, which is a concentric sphere. Clear? And volume density rho, this radius you take R. Okay? So through this sphere, phi out is going to be what? Phi out will be what? By Gauss law we are doing first. U enclosed, there is no choice. Q enclosed by 0. How much charge is enclosed? The volume into rho. But by formula E dot ds is equal to what? You take any portion here, that area vector radially outward only, and electric field also radially outward. E and ds have the same direction. So there it will be over that surface, inner surface, E ds cos 0 degree. E is a constant, it will come outside into ds. Okay? Electric field is constant. Any point on this surface, like that. It is E into how much? All these areas are added, it will give you 4 pi r square. Now compare these two. So if you compare these two fluxes, you write this one as E in into 4 pi r square will be 4/3 pi r cube rho by E0. Clear? Understand? So E is going to be E in. E is going to be what? Cancel 4 pi, 4 pi. So this is going to be rho r by 3 is 0. Field is really outward. You can put a vector over there. E in vector will be rho r vector by 3 is 0. Am I correct? But one more part is left over there. We have to find the electric field strength outside. This is E in, E out we need to consider. Okay? Then to find E out, we will proceed the same method. To find the field outside Gaussian surface is this one. So this point, spherical symmetry is there. You draw the Gaussian surface whose radius smaller. This one remain bigger only. Given, no? So phi out will be what? E out into surface area. That is 4 pi r square. By Gauss law, phi out will be Q enclosed by E0. How much charge is enclosed in this sphere? Its volume is 4/3 pi r cube. Q enclosed. This must be equal to rho. Am I correct? Volume of that multiplied by rho. So there it will be 4/3 pi r cube rho that divided by E0. Clear? Just compare these two. So E out into 4 pi r square r cube rho by E0. So this implies 4 pi get cancelled. So E out will be rho r cube by 3 r square. This is outside the field. See, E out is proportional to 1 by r square, isn't it? But E in is what? What about E in? You got proportional to r. So this is going to be straight line. Here it is going to be what? This graph we did in electric field. Many other places. So it falls rapidly in compared to that proportional to 1 by r. Let us plot the graph. You will understand better. By remembering this thing, due to solid sphere, electric field strength. Okay. E in proportional to r till what? The distance r. If you put for r equal to r, E surface rho r by 3 is 0, and for r equal to r, E out will be rho r by 3 is 0. Why? Because you put small r equal to big r, see no, by 3 0 r square. These two get cancelled. There it will be rho r by 3 0. E out rho r by 3 0. E in rho r by 3 0. So plot the graph now here. Now the graph of E versus R, till R it increases linearly. So plot the graph accordingly. Till distance R it increases linearly. At equal to R it has maximum value. What is it? At equal to R its value is Emax. Rho r by 3 is 0. Then it falls rapidly because proportional to 1 by r square. Clear? So this is electric field due to a charged sphere. Keep this data in your mind. Outside it is proportional to 1 by r square. Inside rho r by 3 0. So many good problems can be solved based on this. For instance, so many years it has come. I told you I will not mention anything particular. You start doing it and then I will help you if you need. Again the cavity problem. Find the electric field inside the cavity. Center of this sphere is given. C1, this is C2. Center of the cavity is placed with respect to the center of the ball by a distance A. This is written by some Russian author, i.e. Irodov. That's why language is a bit different. So this distance they have given A. Okay, you have charged the sphere. It's a non-conducting ball. You have to find, it has volume density. Over the whole volume you can put charge. It is not conducting. If it is a conductor, then what will happen? Charge will reside at the surface, isn't it? So to find the strength of electric field at an arbitrary point inside the cavity, that point be P. Okay? Go by that superposition principle. To find the strength of electric field inside the cavity, go by superposition principle. What is that principle? Remember it, I hope. We'll assume that the whole sphere is charged with positive charge, and this sphere, this smaller one, this one charged with negative charge. So that by superposition principle we can say that when these two volumes intersect, this portion becomes chargeless. Which portion? Cavity has no charge. So we are going to use superposition principle. Already I have explained. I don't want to waste more time. I just want to say that inside the sphere, electric field is rho r by 3 is 0. See how beautifully it can be solved in terms of distance A between these two and volume density rho. This position of the point P from C1, this vector CP1 equal to R1 and this vector CP2, you take this one as R2. C1, C2 as A vector. Distance given A, or we have taken vector. Okay. Now, electric field at P due to the big sphere of volume density rho, we are assuming that no gap is there, no cavity is there, whole sphere is charged. So electric field at P due to big sphere of volume density rho is given by U1 vector rho R1 by 3 is 0. Agree? Similarly, electric field at P due to this small sphere, due to the sphere, its volume density is what? I told you minus rho. Due to small sphere is E2, which is given by minus rho R2 by 3 is 0. Hope you have understood. Am I correct? I think you have understood. There is no problem in it. So it is minus rho R2 by 3 is 0. Now net field at E will be what? Therefore, at P, electric field at P is vector sum of these two, E1 plus E2. This is nothing but rho R1 by rho R2 by 3 is 0. Take rho by 3 is 0 common. R1 minus R2. This is going to be what? In this diagram, this part is A, this is R2 and this is R1. So by triangle law, in triangle C1, C2, P, C1P equal to C1, C2 plus C2P. C1P is what? R1. C1, C2 is what? A. C2P is R2. Clear? Therefore, A equal to R1 minus R2. Clear? You just put it there. EP will be equal to rho into A by 2E0. Clear? So same, sorry, not 2, it is 3. It is 3. 3 is 0. How nicely the problem can be solved with the help of Gauss law. Okay, today till this only. If possible, I will come with another session to discuss more problem on Gauss law, and I'll definitely notify. But those classes going to be live session, I will notify in my channel. You'll be joining accordingly. Okay. So if you have subscribed, automatically you will get the information. If you have not subscribed, you have to check when the session is coming out. Okay. Thank you for staying with me till the end. See you again.